Hi everyone, welcome in the RISC-V booth here in the embedded world. We have a joint presentation today. It's Codasip and MachineWare. My name is Zdeněk, I'm from Codasip, and together with me there is Lukas from MachineWare. And we're going to talk about the fast virtual platforms for custom RISC-V processors. Firstly, let me introduce the companies. So we have a MachineWare here. The main thing for them is to do the virtual prototyping, not only for the CPUs, but for the whole systems as well. So it's about the CPUs and the system, whole stack simulation, or software stack simulations. So it's not about the bare metal only, it's about the whole rich operating system simulation and so on. And not about the simulation only, also about debugging. We will come to that later. And then there is a Codasip. Codasip is focused on the RISC-V CPU development and RISC-V development and also EDA tools by which you can customize these RISC-V CPUs. And then you can enjoy the fact that you can innovate, you can differentiate your RISC-V CPUs in the product. Now, why we are here? So if you look at the semiconductor, we can see that we are reaching the limits. In some cases, the laws even stopped working, such as Amdahl's law or Dennard scaling. We can discuss and debate about the Moore's law, but it's also slowing down at least. So we have to find a way how we can accelerate, how we can get the performance, how we can sort these problems. One way to go is to use some fundamental change, such as new technologies like carbon nanotubes or optics. These things are good, but a bit further in the pipeline. So we need to find a way how we can do it now. And the way that we believe in is custom compute, or heterogeneous compute in general, where we have different things that sorted out different tasks, right? So we have this heterogeneous world. Now, how we can solve this problem, how we can have these heterogeneous blocks done in an efficient way? Well, we can do it in a way that we can have RISC-V CPUs that are tuned, that are customized towards a certain thing. It can be image processing, it can be AI on edge, it can be anything that you can think of. Now the customization is here for a while because you can do customization on several layers. You can do customization on the software, you can do customization in SoC, and you can do customizations in the CPU. And the thing is that you can do it in the old-fashioned way, which means that you can do customization using different teams for compiler, different teams for simulation, different teams for the RTL. But as you can guess, it's a kind of really hard work to do and it takes time and so on. So what if you can automate some of it, if not all of it? And this is exactly where the Codasip comes in with the tooling, because we have tools by which you can do these things. So you can describe your CPU one time and you can get SDK, you can get RTL, and you can get virtual platform as well out of the single description of the CPU. So if we zoom in to the virtual prototype output, now why we need virtual prototypes? Well, we need that for a couple of different reasons. One of them could be design space exploration. We need to have something before the real hardware is developed. We need to explore different options. What if I have this feature in? What if I have that feature in? And I like to see the impact immediately on the software level. I can use also virtual prototyping for the pre-silicon software development. So it's not about the design exploration anymore, but I can do real software. I can do real software stack, the full-blown thing, not only a single application, but I can enjoy the fact that I can simulate the whole software stack. And I can even go beyond that, and I can connect this virtual prototype to the other parts of the ecosystem, such as debuggers or other parts of the Ethernet and so on. And last but not least, if you look at the virtual prototypes on platforms, they scale quite well because you can deploy many different copies in the cloud, for instance. So you can have 10, you can have hundreds, you can have thousands of the same system deployed in the cloud, running different software stack or different software, whatever you would like to run on it. So it scales quite well. Now, if we look at the real example, this is what we did with the MachineWare. So we have a studio, which is the EDA tool in which you describe the CPU. We use codal description, which is our own architecture description language. It's a C-like language in which you capture the CPU on the architecture level as well as a microarchitecture level. So it allows you to generate not only the RTL for the CPU, but also other parts of the software toolchain, such as LLVM-based compiler that's aware of every single instruction that you have inside of the CPU, and it's able to use these instructions fully automatically. Of course, you get the RTL of these instructions as well. you have a standalone simulator, you have verification tools that you can use for the verification CPUs, and now we also generate Sim5 CPU model or extensions for that. So I'm going to hand to Lukas, who will explain more.
I'm going to explain a little bit about this Sim5 CPU model. So in MachineWare, as Zdeněk already mentioned, we focus on virtual platforms, which are full system simulations. And with the generation of this Sim5 CPU model, we can integrate it into our virtual platform. And this virtual platform is basically a digital twin of your entire SoC or board. So it contains not only the generated CPU model of your customer's RISC-V processor, but also all the peripherals around it that you need to execute a complete software stack on that system. So for example, things like an I/O subsystem where you can attach CAN, UART, etc. So we prepared for this event, we prepared a little demo, and this demo is a RISC-V FreeRTOS timer. So it is an application that is a UART controllable timer, so you use the UART of the system to program the timer. The system also has 7-segment displays to output the timer value, and these 7-segment displays controlled via GPIO. So in terms of hardware to run this example, we need, of course, the CPU model. We need an interrupt controller for the interrupts of the peripherals. We need a model of the UART. We need a model of the GPIO controller. So this is our virtual hardware model. And on the software side, we have a RISC-V application that runs on top of FreeRTOS, which is an open real-time operating system. And so what you can do in the demo is you can set the timer value and then the timer will run. Also, of course, we have a customization in the RISC-V processor. And the customization that we have in the RISC-V processor is basically a custom instruction that takes as an input a number that you can see here on the right-hand side, and then it automatically generates the GPIO control signals to drive the 7-segment display to display that number. So a custom instruction that takes this number and then generates the GPIO control signals. And to run this demo, we of course need the full system simulation. So what does that actually look like? So in the demo, we have our target software, which is the timer application running on top of RISC-V FreeRTOS. And we have the target hardware, so our virtual platform, which has the Codal RISC-V processor and the custom instruction that I explained before. From this description, the Codal description, we can generate the software toolchain. So we can generate the compiler that can use our custom instruction. And we feed our target software into this toolchain to generate the target software L file, which is the RISC-V L file. Now we can also generate this CPU model based on our Sim5 technology that has this customization inside, and we can integrate it into our virtual platform that has the hardware models that we need, such as UART and GPIO controllers. And last but not least, we can load the software on this virtual platform and execute it, and that's what I'm going to show right now. So what we can see here is the Codasip Studio tool. So in this Codasip Studio tool, on the right-hand side, we have the description of this custom instruction that does this number decoding written in Codal. And we can now press the SDK button here to generate the software development kit. So, which means we can generate the compiler that can also then utilize this custom instruction that we have added in the Codal description. So the compilation process takes a second, so we speed it up a bit. But now we have the software toolchain ready. Now we, as a second step, can generate this Sim5 plugin, this custom Sim5 model of our RISC-V processor by clicking on the Sim5 plugin button. And now the plugin is generated, and we can see that the tool gives you some configuration files and most importantly, the shared library that contains the simulator code. So now we can start the FreeRTOS demo. And you can see that a couple of windows pop up here at the bottom. On the left-hand side, let me pause it again for a second. On the left-hand side, we see the output of the virtual platform. So this is a combination of the logging output and also the output of the UARTs that we have in our virtual platform. As you saw in the previous graphic, the virtual platform has two UARTs. One is used for logging and one is used for the user interface. And of course, to drive these UARTs, we use the FreeRTOS driver code, the original FreeRTOS driver code. So now we can start the timer by interacting with the system through the UART. So we start the timer with a value of 12, and now we can see in the logging how the GPIO controller drives the 7-segment display. And of course, for each number that you see displayed on the 7-segment display, the custom instruction that we added is being executed. So in summary, what we have shown you today, RISC-V is an ideal solution for custom compute. So if you want to build a custom processor, RISC-V is the way to go. And with the integrated solution that we have built together with Codasip, you have an easy entry in your custom RISC-V design. You can design your custom RISC-V processor with Codasip Studio and then generate a fast simulation model for integration in a full system virtual platform, which allows you to start all the software development and analysis long before you even have a hardware prototype. As we said before, virtual platforms enable full system hardware-software co-design because you can take all system-level aspects into account when you look at the customization results of your simulation results for your customized RISC-V processor. And of course you can do the pre-silicon software development and testing, and you can integrate with other simulators and other tools. So I think that's it from our side. Thank you very much, and if you have more questions or would like to learn more about this, we invite you to come to our booth.